the next topic that we want to do in vectors refers to vector integration, and here we will talk about three kinds of integrals that are commonly seen whenever dealing with vectors. Okay. These are line, surface and volume integrals, okay. And I will go over these briefly. Okay. There are a lot of interesting relations involving that relate these integrals to each other, but we will not be discussing that. I will just give you the definitions of these three ways of doing integrals, and you will see that in lot of your courses you will be using some of these integrations. Okay. So, here what we want to do is we want to do an integral. See typically we do an integral of a function over a variable. This is what you do, this is the usual integration of a function of a single variable. Okay. Now, what we want to do today is try to see, is there a way to define integral of maybe a function of a vector over a vector. How can you define such quantities? Okay. It turns out that there are different ways to do it, and as we said that your R, okay, again we are restricting to three dimensional space. So, R is has three components x, y and z. So, your dr will have three components dx, dy and dz. Okay. And so when you do this integration over dr, okay, you can do it in different ways. You can do things called line integrals, where you actually integrate along a certain line. You can do a surface integral where you integrate over the vector. The vector can be anywhere on a surface, or you do a volume integral where your vector can be over an entire volume region. Okay. So the basic idea is the following. So, suppose you have x, y, z, okay, and your r is some vector that points anywhere. So if you have your r vector, okay, now when you integrate r vector, you can either integrate along a line. So you take all possible r values along this line. That would be something like a line integral. So you integrate the function along this line, that would be a line integral, or you could take r and integrate over an area. So you take all possible values of r that can be in this area. So r can be anywhere here, it can be here, 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 here and so on. So that would be integral over an area, or you could integrate over a volume. So or you could take something like this. You could take some region and you say that r can be anywhere in this region. So these are the three kinds of integrals that you will see. So this would be a volume integral, this would be a surface integral, and this would be a line integral. Okay. So what I want to say is that your integral of this function, okay, you can look at all these kinds of integrals, okay, and what I will try to do is to give you certain definitions of these integrals. Okay. Now, it turns out that there are many ways to define some of these integrals. Okay. So you know, based on the context, okay, these integrals are defined in different ways. Okay. I will just show you certain definitions and you can easily do the other derivations. So, let us start with the line integral. Line integral is also sometimes referred to as a contour integral. integral or a path integral. Okay. So, here what we have is some function of x y z, okay, and let us for convenience take this as a vector field. Okay. So, and then you want to integrate it over a path. Okay. So, you want to integrate it over the vector. Okay. So, integrate you want to integrate this function over this variable, and the change of this variable goes along some path c. Okay. So, this is what you are going to do, and the line integral is defined in the following way. So, you can define the line integral as f dot dr along path c. Okay. So, what does this path represent? Okay. So, this path could have an initial point and a final point. Okay. So, this path can go from A to B along the path C. So, the path is C. Okay. So, then I would write this in the following way. So, what I could write it is slightly differently. I could write from A to B along path C. You could go from A to B along another path, that would be a different line integral. So, this is an example of a line integral or a contour integral. Okay. Now, notice I had a vector field f and I took a dot product with this vector differential dr. Okay. So, now when I do this, when I take I can expand this out. So, if my f has components f x, f y and f z, and my dr has components dx, dy, dz, okay, then you can clearly see that this integrand for the line integral has the components. So, I can write this integral a to b f x dx plus f y dy plus f z dz. And since f was a vector field, f x, f y and f z are all components of x are all functions of f x, y and z. So, each of these, so f x is a function of x, y, z, f y is also a function of x, y, z, f z is also a function of x, y, z. So, all these are functions of x, y, z. Okay. And so all you are doing is you are taking you are doing this integral, you are integrating over dx, okay, along this contour. Okay. Then you are integrating this function over dy along the again along this contour, and then you are integrating this over dz again along this contour. Okay. Now, it looks easy to write, but in practice it is actually a little tricky to implement, because you have to ensure that dx, dy and dz are along contour. Okay. So, your differential change in R, okay, you cannot take arbitrary differential change in R, you have to ensure that these three are they follow the contour C. Okay. And we will see examples of this. So, we will see how to do this in practice. Okay. But basically this is something you have to ensure when you are doing line integrals. Okay. You can, I mean, line integrals can also be defined in 2D. In 2D, so in 2D you could have integral from a to b along contour C f x dx plus f y dy. Okay. And this is something that is a little easier to, at least in 2D it is easy to show the path, show the contour C. So, if you have this x y plane in 2D, okay, and if you have a point A and you could have a point B, and you could have your contour C might be some sort of path that goes from A to B. Okay. So, you could just have a contour that looks like this. This is my contour going from A to B. Okay. You could also have other contours going from A to B. You could have something that looks like this, another contour. You could have something that looks like this. Okay. So, there are different contours that you can have going from A to B, okay, but you can show this, and you can show it nicely in this 2 dimensional space. Okay. So, let's go into the other kinds of integrals that you can do, okay, and then we will come back to some issues with this line integral, some interesting aspects of this line integrals. So, the other integral that we talked about is what we called a surface integral. So, here what you do is you define, you take integral, and let us say you take f, some vector field. Okay. Now, you dot it over now I will just write it as ds vector. Okay. This is called a surface element. Okay, and this integral is over some surface, I will just call it sigma. Okay. So, what you are doing here is you define something called a surface element. So, ds is basically your surface area d sigma, which is a scalar dotted times the normal. Okay. So, the idea is whenever you have a, if you have some sort of surface like this, okay, then you can define a normal to the surface. Okay. So, this is my very small element ds. Okay. So, ds equal to d sigma, which is this infinitesimal area times this normal element. Okay. So, the idea is if you go back to what we had shown, the way we had shown the surface integral. So, you have a large, you are integrating over the region. So, you break it into small differential elements, okay, such that and each one has a normal, okay, and you have this d sigma. Okay. So, that is the differential surface element. Okay. And so your ds is nothing but d sigma into n. N is the normal to the surface at that point. Okay. So, your surface integral is defined in this way. This d sigma is usually can be represented in terms of, if you are in 2 dimensions, you can represent it in terms of dx and dy, okay, and you can usually calculate this surface integral. Okay. Again you will see some of these when you are dealing in quantum mechanics. Okay. Let me mention the third type of integral, and this is also something that you see regularly in quantum mechanics. Okay. That is the following, that is a volume integral. So, here what is done is you take a scalar field, okay, and then here we are particularly referring to 3D volume integral of a scalar field. Okay. So, this is so you take a scalar field f, and you multiply it by a differential volume element dV, and you integrate over this volume over some region, I will just call it V0. So, this is so what you are doing is you have some sort of infinitesimal volume element dV, okay, and you want to integrate over this some volume V. Okay. So, you are integrating over some volume, this is a 3 dimensional volume region. Okay. So, maybe show it this way. Okay. And you want to integrate the function over this region. So, what you have is you have a you typically define it for a scalar field. Okay. So, the scalar field is this, and this is nothing but your scalar field is a function of x, y, z, and the differential volume element is nothing but dx, dy, dz, and you integrate it over this region. So, this is actually a 3 dimensional integral. Okay. So, that means you have to take this function, integrate it first with, I mean you have to do 3 integrations. Okay. And your volume region, you have to make sure that the boundaries are such that they define the volume V 0. Okay. So, these are the 3 integrals that you see most often. Okay. And let us just go back, the surface integral. Okay. So, this d sigma usually can be written as dx dy. Okay. And so you have a 2 dimensional integral. So, this is a 2 dimensional integral. Okay. So, we saw that the line integral, so you can go from point A to point B, you can go along different paths, along different contours, and in general the line integral is dependent on the path, it depends on which path you go through, you will not get the same answer, but under certain conditions, okay, you get the same answer, you get an answer that is independent of path. Okay. So, I just want to mention this, okay, and you can easily find out what are the conditions. Okay. So, there are conditions for path dependence or path independence of line integrals. So, the question is, when are these line integrals dependent on the path and when are they independent of path? Okay. And this will sound familiar to you, okay, for those who have taken who have seen thermodynamics. Okay. So, you learn in thermodynamics, so you learn about path dependent quantities like work and heat. Okay. So, what we learn in what we do in thermodynamics is that you write your differential work as minus P times dV. Okay. And now what you do is, you to calculate the work done in any process, you have to do an integral minus P dV. Okay. And this integral is over some path, it goes from some initial condition, let us say P 0 V 0 to P 1 V 1. So, it goes from some P 0 V 0 to some P 1 V 1. So, you go along some path, okay, and this is in general, this is path dependent. Okay. And there are very sound mathematical reasons why this is path dependent. Okay. But basically this work is the quantity that is in thermodynamics. Okay. We say work is a path dependent quantity. Okay. Now, in potential theory, okay, so you write your work dW as F dot d you can, so it is some force times some displacement. So, it is a force dotted into displacement. So, this is your force and this is a displacement. And again your work done is actually integral f dot dl, okay, over some path. Okay. So this is a line integral. So, your work is a line integral, okay, and what you have to you can ask the question, when is this line integral independent of path. Okay. So, when is w independent of path? Okay. Now, it turns out that you can give a very straightforward answer to this. Okay. So, answer is when f is equal to minus gradient of some potential. Okay. So, so when there exists a potential energy function V of x y z such that f of x y z is equal to minus grad V. Okay. Okay. So, when you can write this, okay, then you can write w as a contour integral of minus grad V dot I will just write, instead of writing dl, I will just write it as dr. Okay. And what we said is that gradient of V dotted into dr is nothing but the differential change in V going along that path. This is nothing but the V at so if you are going from point A to point B, then this is nothing but the potential at B minus the potential at A. This is clearly, this is independent of path. So, whenever you can write a potential energy function, then the work done in going from any point to some other point will be independent of the path taken. Okay. And this is a very fundamental idea in all of physics, that whenever you can write a potential, okay, then your force is said to be path independent, okay, and this leads to a lot of nice relations. Okay. That means you go from one point to any other point, okay, then the work, whichever way you go, the work will always be equal to the difference in the potential energy. Okay. So, so whenever you can write a potential energy function, you know that the work done in say displacing a particle from one point to another will be independent of the path taken. Okay. So, I'll stop the discussion on vectors here. Okay. So, in the next class I will do some practice problems, okay, where you will see application of some of these concepts. Thank you.